Hey guys, this video is about the chapter Entropy and Gibbs free energy, which belongs to A-level chemistry syllabus. Now in this video, we will go over the entirety of this topic while keeping the learning outcomes as specified in the syllabus in mind. And we will be utilizing three different sources. We will be using the Chem Guide page about entropy and Gibbs free energy, and we will be using the Knock-Hardy presentation about entropy and free energy, and we will also be using this book called Cambridge International AS and A-Level Chemistry by Laurie Ryan and Roger Norris. Well, let us proceed. Firstly, are any of you aware of what exactly entropy is? Because in the beginning we have to be able to define it. You don't necessarily have to be able to completely grasp the concept, but we need to begin somewhere. Well, entropy can be defined in a number of manners. We may say that entropy is a measure of the randomness or disorder of a system. Right? This is one of the definitions. And another may be that it is a measure of the number of possibilities. And what those possibilities are, we will understand later. Another definition for entropy is that entropy is a measure of the dispersal of energy at a specific temperature. And from this definition, something gets into our mind, and it is something we should ensure that it stays there. The fact that a specific temperature has been mentioned, and the implication is that the value of the entropy will differ at different temperatures. So keep this in mind for the moment. And we may have other definitions of entropy, and for example, entropy can also be thought of as dispersal of energy, meaning the spreading out of energy is also entropy, either from the system to the surroundings or from the surrounding to the system. Again, this is something important. For those of you for whom chemistry is not a new subject, you will realize immediately that from the system to the surroundings most likely implies an exothermic process, and from the surrounding to the system implies an endothermic process. And here it becomes clear that there is a link between exothermic and endothermic reactions and the entropy of a particular reaction. Well, before moving onwards, we will have to define what a system and what a surrounding is. Well, a system may be defined as the part that is under investigation, that is being examined, that we are considering. And here is the definition. And if we were to talk about a particular reaction, and because in chemistry we are dealing with the chemical reaction, and the chemical reaction itself is basically the system. For example, for the reaction of magnesium with sulfuric acid, the system is both the reactants and the products. So the system of magnesium reacting with sulfuric acid, and the system is basically the magnesium and the sulfuric acid and the magnesium sulfate that is being produced. And this is basically because this is what we're examining, because this is the chemical reaction, the components of the chemical reaction which we're investigating, and hence we term them as being the system. But in all of this, what is the surrounding? Well, the surroundings is basically what is surrounding the system. And what could the surroundings be? It could be the solvent. In the case of magnesium and sulfuric acid, reacting the solvent would have been water, because the sulfuric acid is most likely aqueous. And then it could be the test tube itself, the test tube in which we have the magnesium, the sulfuric acid, the products, as well as the solvent. Or it could be the air that surrounds the test tube, that is also a surrounding. And anything that is dipping into the test tube but not partaking in the reaction itself, for example a thermometer, could also be thought of as the surrounding. And hopefully I have clarified these two terms, system and surrounding. And we have also talked about the definition of entropy as being a measure of the randomness or the disorder of a system, or a measure of the dispersal of energy at a specific temperature, and the significance of temperature has been introduced, and also the fact that exothermic and endothermic seem to have a relationship with the entropy as well. Now, what is a spontaneous reaction? A spontaneous reaction is basically a reaction that, when once has begun, will continue to proceed without any external influence needed to drive it forward. And one might assume that spontaneous reactions will be pretty quick, but they are often not, although they can be, because the only requirement for a reaction is to be spontaneous is that when it has begun, it will continue to move forward, and this continue to move forward will not require an external push, will not require, for example, continuous input of energy. However, spontaneous reactions often do not start by themselves. They often require an initial input. For example, if we were to consider the reaction of methane with oxygen to form CO2 and H2O, the reaction is spontaneous. Why? Because when the reaction has begun, it will continue until either all of the CH4 has been used up or all of the O2 has been used up. And for this to continue, there is no push required. However, for this reaction to begin, to start in the first place, we do need an initial input of energy, and this initial input is often light. Hopefully you're a bit clear on the spontaneous, and it can be quick and it can be a slow process. Another thing, that the system becomes energetically more stable when it becomes more disordered, meaning if the value of the entropy is greater, then the system will be energetically more stable, and the system prefers it that there is more disorder, and the universe is actually moving towards greater entropy. This is happening literally all of the time because it wants to be more energetically stable, and therefore it wants to have greater entropy. And this is how feasibility comes into play. Whether a reaction will happen or not is closely linked with the entropy, the total entropy. Right, now chance and spontaneous change. Perhaps at the moment you aren't all that clear about what entropy is. As mentioned previously in the definition, it is a measure of the disorder and the randomness. However, this definition can often be misleading, although it is completely accurate. If you were to write it down in an A-level exam, you would get full marks, but often when we read it for the first time, it makes us go in a direction which is absolutely false. For example, if we were to have a system which composed of 5 books and another which consisted of 5 other books, and one of the systems had the 5 books stacked neatly one over the other, and the other had a more disordered state. They were tilted at various directions relative to each other. And so which one of them will be more disordered? Yes, we would, at the right on spot, we would say the one which had the second one. However, your reasoning might be wrong. Is it more disordered because it is more messy? Well, no. It is more disordered because there are a larger number of possibilities, a larger number of orientations for the 5 books. There is only a few ways for 5 books to be neatly stacked. Might even be one. However, when we talk about something that can be randomly arranged, someone told us that we can arrange it randomly, there are far many more possibilities. We can arrange it in whatever way we want as long as it is random. However, if someone were to tell us that we have to stack it up neatly, there aren't a lot of possibilities, and therefore the value of the entropy is lower. Whereas in the second case, that is the one in which we will allow to be much more random in our organization, has a lot more possibilities, a lot more different arrangements, a lot more flexibility in how we can arrange them. And this is basically what entropy is. And in the Chem Guide page, there's actually a pretty interesting use of analogy to explain all of this. But we won't deal with this later. We'll deal with this later, when that is being less of a bother. Now, when you talk about diffusion, if you were to consider an example of diffusion, why does something diffuse? Because it wants to have a greater number of arrangements, it has to occupy more volume, and this will increase the entropy. However, we're not talking about this at the moment. At the moment, we will be going in a completely different direction. So if you were to spill a few drops of perfume, it would eventually spread throughout the room. And they will move randomly, the molecules, that is, in straight lines until they collide with air molecules, other perfume molecules, or the walls. And eventually, this random movement and random collision will result in a complete spread out. And again, this spreading out has a lot to do with the laws of chance and probability. As in, why is the thing spreading around? Why isn't just staying put together? There isn't any sort of external force in play. There isn't any draft because all the windows are closed. So why the hell can't they just stick together? Why such animosity? Why are they moving apart? And then we come to something called the laws of chance and probability. Has a lot more to do with entropy. Has a lot to do with the various types of arrangements. So if we were to take a look at figure 23.2, we have two flasks, and they're connected by something called a stopcock. And one contains helium and the other contains argon, and the gases are basically inert. And when we open the stopcock, the gas atom will move spontaneously by diffusion, and the gases will become mixed up, and there is more disorder. But let's not consider why there is more disorder. Let us consider why they have moved. But then again, this also has something to do with entropy. The reason is that because when we remove the stopcock, we have given this system greater entropy. Why? Not because this mixing up has taken place. That is one possible state. We have given the system entropy. Why? Because we have given it a lot of different possible arrangements, and this entropy is given the moment the stopcock has been removed, because we have given the entire system a lot of different choices, a lot of different possible orientations, a lot of different possible arrangements. And this is why the entropy has increased, and this is why the disorder of the system has increased. Alright? Because we have given it choices. And this has to do with the disorder part of it. Alright? But again, why do they diffuse in the first place? Why are they diffusing? Why did they spread out? Isn't it a possible arrangement? As I said, there have been a lot of possible arrangements that they might stick together right where they were. So why doesn't it happen? Why is it something so unlikely to happen that most often we don't even talk about it? Why not? Isn't that a possible arrangement? We have given it a lot of entropy. We have given it a lot of arrangements. The reason is simple enough, because we have given it so many different orientations, so many different possibilities, and each orientation has the same likelihood of happening, and the possibility of them sticking right where they were, or all of them clustering in the same flask, is very little compared to the possibilities of them arranging themselves in a mixed up situation in different orientations. For example, 3 purple here, 4 green here, or 4 purple here, 3 green here, and whatever. The possibilities of them mixing up in different ratios is much more, there are much more possibilities, there are much more possible arrangements than for them sticking together. And that is why diffusion and spread out happens, because they're much more likely to happen. This has a lot to do with probability. Hopefully, again, this is making sense to you. We can quickly go over this explanation. Diffusion and number of ways. We can show that the molecules in a vapor diffuse by chance by thinking about the possibility of finding them at one place at any one time. So what is the possibility that a particular molecule will be at one place in a particular time interval? We have to consider a simplified model, this one, and there are 3 molecules in gas jar A and they cannot move into gas jar B because of the partition. And we're assuming 3 things. Number 1, there are only a few molecules, 3 to be exact, in gas jar A, and that there are no other particles present in either A or B, and that when the molecules move, they will move randomly and change directions when they collide. And this is basically kinetic model theory, whatever. So after the partition has been removed, the molecules can move randomly not only within A but also within B. So there are basically 3 molecules and 2 places in which they can be. And what are the number of ways of arranging the molecules after removing the partition? They're basically 8 ways. And this is why the entropy has increased, because initially there was only one possibility, one possible orientation. One possible orientation, one possible state of being, one possible arrangement. However, what happens now? There are 8 possible arrangements. The entropy has most definitely increased. And this is what most reactions want. They want the entropy to increase. They want to go in a direction that will increase the entropy. Again, keep this in mind for further study. Right, so how do we figure out mathematically how many possible arrangements there are? Well, we use a formula called x raised to power n, where x is the number of different places molecules can be and n is the total number of molecules. And 2 raised to power 3 is, as we are aware, equivalent to 8. So, and if we scaled up this number, that is 3, to the number of gas molecules that we might actually find in a container in the lab, the number of ways of arranging the molecule is extremely large. For example, for 1,000,000 molecules between 2 gas jars, it would be 2 raised to power million, and a number that is so large that our calculator, the scientific calculator we normally deal with, cannot actually have it. So huge a number. And so, why does diffusion occur? Diffusion occurs because the likelihood of molecules spreading out is so much more than them sticking together. This has a lot to do with likelihood. And therefore we are actually talking about 2 things at the same time: entropy increase, and the fact that there is so much entropy is also why spreading out is more likely to happen. Hopefully you understand this. The greater the number of molecules, the greater will the likelihood of diffusion spreading out be, because the greater will be the number of possible orientations, and therefore the probability of them sticking together compared to that of the total number of orientations will get less and less, negligible to negligible. The idea of the number of ways of arranging either molecules or the energy within molecule dictates whether changes that take place are the ones that are most likely to happen. And I think all of this concept has applies in this scenario to a physical process, but most certainly the same thing applies to chemical processes, although it is a bit more complicated. Right, so we should do this question. Which of the following changes are likely to be spontaneous? Number 1, sugar dissolving in water. Think about it. Have you ever tried to dissolve sugar in water? Do you think it is spontaneous or not? Well, no. Reason being that you have to continually keep stirring it for all the sugar to have dissolved, and therefore it is not spontaneous because it needs an constant external pull, or you might have to continue heating it for the dissolution to take place. Next, this is again an example of diffusion, most certainly spontaneous. Water turning to ice at 10 and ethanol vaporizing at 20. You should remember that the boiling point of ethanol is actually 78. And ethanol vaporizing at 20, this is an evaporation process. And evaporation will most likely need continuous heat from the surroundings. And the same goes for water turning to ice at 10. This is likely to require a change in the pressure from the normal atmospheric conditions, and therefore we need a continuous pressure acting on it. And the change of state always requires something, pressure to be acting on all of this, because if pressure changes, the state change will not take place. Water mixing completely with cooking oil, not spontaneous, reason being that the two of them are immiscible, and unless we're using a lot of energy and continuing doing it, they will never mix together. If we keep on stirring it, it will be mixed. But the moment we stop stirring, they will become different layers. They will separate out into two different layers because they're immiscible. Normally, they cannot mix together. Limestone decomposing at room temperature. Spontaneous because you'd have to give an initial input, but it will continue doing what it is doing afterwards. We won't require to give them constant supply of heat, because if we give it a high enough heat, it will continue decomposing. We will look at the answer of these later to make sure that what we said was right or not. Now for a pause. In, and then you drop them on the floor, and every time you did this you would get a different random pattern of coins on the floor arranged just by chance, and that would be a disordered system. Now it is just imaginable that when you dropped them by chance they would fall into a neat stack of coins like the one you started with, but the probability of this happening compared to all the other ways that the coin might fall in a disordered way is so very tiny that you would be totally amazed were it to actually happen. Again, I think this is a pretty great analogy because this has a lot to do with chance. Because there's a lot of entropy in this particular process. That is the process of dropping a stack of coins. There's a lot of entropy. Why? Because when we drop it and it eventually reaches its final stage, there's a lot of possible orientations and therefore a lot of entropy. And that is the reason why there is so little negligible chance that it will be a stack at the end, because the entropy is so high that the possibility of this one orientation compared to all the other possibilities is very low. Right, let's just go over this quickly. Technically, entropy applies to disorder in energy terms, not just to disordered arrangements in space. But we won't be really doing this a lot. But we often just quickly look at how disordered system is in space in order to make a judgment. More disordered in the way that energy is rearranged as well. Suppose you managed to arrange some gaseous molecules in this container so they were all exactly evenly spaced out and that they all had the same energy. That is a fairly ordered state. And then you let them go and do what molecules do, move around and bump into each other. And the collision will cause them to change direction and it will probably speed up some of them, slow down others. After a very short time, their arrangement in space will be chaotic. and so will the way energy is shared between them, because there won't be any pattern. One molecule that is 5 centimeter to another one will have very much high energy and next moment. So there's a lot of possible orientations, right? So the entropy has increased in terms of the more random distribution of the energy. This is basically all you need to know at this level. Hopefully, the concept of entropy and that of chance and probability and why diffusion happens and stuff like that has become clear to you. Right, back to the book. Now, when we come to compare entropy values, how do we do that? Firstly, when we are comparing the entropy values of different substances, we need to make sure that our comparison is fair, because otherwise there won't be any reference, and the reference is that all of these entropy values are taken at standard conditions at 298 Kelvin, which is basically 25 degrees Celsius, at a pressure of 101 kilopascal, and in the states in which they usually exist at the given temperature and pressure. And moreover, we consider these entropy values for 1 mole of a substance. Now, basically, what is the SI unit for a something called standard molar entropy? What would that happen to be? Let's take another. What do you think that would be? Well, it would be joule per Kelvin per mole. And why is it standard? Molar entropy standard because we are taking the conditions to be standard, molar because we are dealing with 1 mole, and therefore our what should we say, our it's joule per Kelvin per mole because we're dealing with 1 mole. Why per Kelvin? Because obviously the condition is constant and joule. And if we were to define standard molar entropy, it is the entropy of 1 mole of a substance in standard state. Pretty easy definition, and this symbol indicates that the entropy is in standard conditions. Trend would be seen for a diamond and a graphite. Both of them are composed of the same kind of atoms, that is carbon. The arrangement is different. Diamond is 2.4 whereas graphite is 5.7. Calcium is also solid, however has a value of 41.4. Lead is again solid, but it has a greater value, 64.8. Calcium oxide, being a solid, has a lower value than both calcium and lead. Calcium carbonate has a higher value than any of them. Mercury is a liquid and yet has basically more than some of the solids. And what is all of this? Well, we'd have to memorize some general rules, right? Remember, number 1, the value of all standard molar entropies are positive. They will always be positive. Whether it is an element or a compound, the value of the standard molar entropy will always be positive. And we might be confused about this because when it comes to the enthalpy of formation, the value for an element is 0. And I wouldn't blame you if you get confused, but this is why I'm stressing again and again. Remember, the value is always positive and never 0. Right, there are some generalizations. Obviously, there will be exceptions to it, but if you memorize the general rules, they will work most of the time. Gases will generally have higher entropies than liquids and solids. There will be exceptions, however, because calcium carbonate, which is a solid right here, has a entropy of 92.9, whereas mercury, a liquid, has an entropy of 76, and this is defying the generalization because the liquid has a lower entropy than the solid. Alright, and simpler substances that have fewer atoms, simpler molecules with fewer atoms, generally have lower entropy. For example, if we were to compare calcium oxide and calcium carbonate, both of them are at the same state, but calcium oxide, which is made up of just 2 atoms, has a lower entropy than calcium carbonate, which is made up of 5 atoms. And then we can also compare carbon monoxide and carbon dioxide. Carbon monoxide with 2 atoms has a lower entropy than CO2, which has 3 atoms. And if we were to talk about similar substances, the substance which is harder will have the higher entropy, will have the lower entropy, because their internal arrangement is likely to be more rigid, and this is why there will be a lower entropy. If we were to compare diamond and graphite, which is softer and much more malleable, if we were to push it with a lot of force, even the layers slide over each other, has a higher entropy value than diamond, even though they're both in the same state and both are composed of the same type of atoms, and might even have the same number of atoms also. Right, another thing is that change of state will always result in a considerable jump in the entropy. For example, if we were to compare H2 in the solid and H2 in the water state, there will be a lot of difference, and this difference will be so much huger when we talk about H2, which has just become a liquid, and H2, which has just become a gas. And there are 2 reasons for this, because not only does the temperature has to rise from 0 to 100 or 1 to 100 depending on the temperature, and temperature change is directly correlated with entropy increase, but also the change of state itself matters, because when entropy changes, the amount of flexibility of movement increases, and this amount of flexibility increases drastically when change of state happens, especially the liquid to gas one, and therefore there is a huge increase. The same amount of change is not visible when change of solid to gas, solid to liquid. However, there is still a drastic increase. Now let's read about this. For a given substance, the entropy increases as the solid melts and then changes to a vapor. This is a general rule. From solid to gas, solid to liquid to gas, there will be an entropy increase. For example, the molar entropy of ice just below its melting point is 48. For example, at -1, the value is 48, and the molar entropy for water is 69.9, just above its boiling point. And the molar entropy for water is 69.9, and this might be just above 0. But just above its boiling point, the value increases to 188.7. So it is 69.9 in the water state, but it is 188.7 in the vapor state. And there is a gradual increase in entropy as the temperature of a substance is increased, and increasing the temperature of a solid makes the molecules or the atoms or the ions vibrate more increasingly, and therefore increases the entropy, because it increases the disorder of the particles. And when a substance melts or vaporizes, there is a much larger increase in the entropy, because there is a larger increase in the disorder of the particles. Hopefully this is making some sense to you. Right, again let's move on to the Chem Guide page. Might be helpful. Right, change of state includes solid to liquid, liquid to gas, and solid to aqueous. And this is something we didn't mention previously, the solid to aqueous part. Entropy is given the symbol capital S. Standard entropy is measured at 298 Kelvin. 1 bar, which is basically equivalent to 101 kilopascal, is given the symbol S0. Right, might find the pressure quotient as 1 atm. Don't worry about it, they're nearly the same. 1 bar is 100 kPa, 1 atmosphere is 101.325 kilopascal. And basically we'd have to use the unit that is recommended in our syllabus. You should check this out. And now we have some standard entropies for a few solids, and they all have the same units. carbon, diamond 2.4, calcium 41.4, CF 68.9, and CaCO3 92.9. And they all have low entropies. Why? Because they're highly ordered solids. But we can notice that the entropy is increasing as the solid is becoming more complicated, as it becomes to have more atoms and more variety of atoms. Also, what happens during change of state? And these are the figures for water in different states. Ice is approximately 48, liquid water is approximately 69.9, and steam is about 189. And the entropy increases as the molecules become more disordered as you go from one state to the next. And notice that there isn't a very big jump in entropy when ice turns to water. And what is the reason for this? That is because the hydrogen bonding between the liquid molecule imposes a fair amount of order on them even in the liquid state. And for benzene, we have liquid benzene is 173 and benzene vapor is 269. And the values are much larger for benzene than for water, and this is pretty obvious. And the reason is benzene is far more complicated a molecule. It is 6 carbon ring with hydrogens projecting from it, and there is more ways of arranging the energy of the molecule in a disordered way over bigger molecules than smaller ones. Right, so moving onwards, what if we were to dissolve an ionic solid in water? Ionic solid is highly ordered, therefore relatively low entropy. Pure water will have a certain amount of order, but when the solid will dissolve in water, the whole system will become highly ordered, as the crystal will break up and the ions will find their way in between the water molecules, and therefore the hydrogen bonding that is making it to be even then quite ordered is broken up, and therefore the entropy will increase. Right? Hopefully this makes sense. Why liquid water doesn't have that much entropy? This has to do with hydrogen bonding, which keeps the water molecules pretty close to each other and restricts their flexibility of movement. Right? Entropy changes when temperature changes. Obviously, if increasing the temperature involves a change of state in the material, then you will have increased the entropy. But we've already looked into that. Suppose there isn't a change of state. Think back to having some gas particles in the container with a high degree of disorder both in their spatial arrangement and in their energies. They're moving in all sorts of different speeds, changing all the time. And if you add more energy, the number of different possibilities for arranging the energy over the molecule increases, and so increasing the temperature will increase the entropy of the system. Right? And this is what we studied till now. So basically, why there is a change in entropy over states, and why this change of entropy over change of state from H2 solid to liquid isn't as significant as in most other particles, and why dissolution of an ionic substance in water causes a highly disordered mixture, highly disordered solution to be obtained. Right. Now when we talk about entropy changes in reaction, previously we talked about the standard molar entropies of an element or a compound, the fact that they were always positive, and why we called them standard and molar, and also why there were different entropies for different substances, and the entropy values link with state, link with the temperature, link with the number of atoms, stuff like that. And right now no reaction is taking place. We may be talking about a single element or a single compound, and we might be heating it up, cooling it down, or we might just be inducing a change in state. But now what if we were to actually partake in a chemical reaction, and how would entropy be involved? Well, when you talk about a reaction and the total entropy change, we will have to compare the entropies of the reactants and the products, and you would have to explain the magnitude of the entropy change, whether it increases or decreases. There is an assumption that gases have high entropy compared to solids, and therefore if there is a change in the number of gaseous molecules as part of a reaction, we can safely assume that there is a significant entropy change, because gaseous molecules carry a lot of entropy or have a lot of positive entropy, because we associate high entropy with gases, and therefore any change in the number of gaseous molecules over a reaction is likely accompanied by a veritable change in the standard entropy. Right, so when we talk about the decomposition of calcium carbonate to calcium oxide and CO2, it is safe enough to guess that entropy is increasing because we're getting a molecule of CO2, which is a gas, and gases have significantly higher entropies. Moreover, we're getting two products from one, the number of products has increased. And when we get 4 molecules of NO2 and 1 molecule of O2 from 2 molecules of N2O5, again there is an increase in entropy, reason being that we initially had 2 gaseous molecules and now we have 5 gaseous molecules, and there is an increase in number of gaseous molecules. Moreover, the overall number of molecules has also risen, and because of that it is safe enough once more to assume that entropy has risen. And we talk about the reaction of nitrogen with hydrogen to get ammonia, we should expect a decrease in the entropy of the system because there is a reduction in the number of gas molecules as the reaction proceeds. So the entropy change of the system is negative, and the reactants hydrogen and nitrogen are more stable than the product ammonia. Again, this is something we should be keeping in mind. And there's basically a lot of questions here. We have to explain the difference in the entropy of each of the following pair of substances. We are comparing bromine and iodine, and in this scenario it is a change of state which has led to the difference in the entropy. Hydrogen and methane, the difference in the number of atoms is responsible. Mercury and sodium has to do with the state. SO2 and SO3, actually the number of atoms has been overridden by the state, and therefore SO2, despite having lesser atoms, has greater entropy. And then question number 3 is about, we have to suggest whether the reactants or the products will have higher entropy, and the scenarios in which it is difficult to judge. In the first one, we can easily judge that it is the reactants who have the higher entropy. In the second, it is probably the reactants with the higher entropy because we have more molecules on the reactant side, and one of the molecules happens to be in the liquid state. And in C, it is possible that the reactants once more had higher entropy because we have a gaseous molecule in the reactants which is absent in the products. In D, it's likely that once more reactants have higher entropy, and again we have a gas. In E, it is a bit more difficult to judge, but probably it is the products who have higher entropy, because whereas we have gases on both sides, on the product side we have 2 gases, whereas on the reactant side we just have 1 gas and 1 solid. In F, it is difficult to judge because we have 2 molecules of gases on either side. When it comes to G, it is probably the products with higher entropy because compared to liquid, aqueous have more entropy and gases definitely have more entropy than solids. And in H it is the products with higher entropy because we have CO2 gas there, which is absent. Gas is absent in the reactant side. And so basically, if we were to go to the chem guide page, and how are we to predict how entropy will change during reactions? So we are dissolving NaCl, and this is a crystalline solid going into solution. The solid is highly ordered, whereas the solution is disordered, and therefore we have an increase in entropy. And if we were to go from H2 gases to H2 liquid, the water is changing from the highly disordered gas into the more ordered liquid. Entropy is falling, and then there is the reaction combustion of methane. We have 3 molecules of gas on the left hand side, but only 1 on the right. 3 molecules of gas here and only 1 on the right. And the starting material are more disordered than the products. And so there is a decrease in the entropy. Notice that if the water had been formed as steam, you couldn't easily predict whether there was an increase or a decrease in the entropy because there would be 3 molecules of gas on each side. And this is important and has a lot to do with the fact that entropy values change at different values of temperature. And this will be linking in with the entropy of the surroundings, because at the moment we're only dealing with the entropy of the system, and actually it is the overall entropy which results in something being feasible or not, something happening spontaneously or not. So this example 3, all of it is something that is good if you keep it in mind. And if we are going on to example 4, which is basically copper sulfate and water, and this is hydration, and the presence of the 5 moles of liquid water on the left hand side means there will be far more disorder before the change than the after, and therefore the copper sulfate crystals formed will be very ordered and the entropy has fallen, because we have a total of 6 here and 1 over here, and lesser number of atoms mean a decrease in the entropy. Hopefully this was helpful. Entropy changes in reaction involving at least some gaseous molecules. As mentioned previously, gases have higher entropies than either solids or liquids because they have a more disordered movement. During a reaction in which there is a change in the number of molecules of gas present, entropy will change. Heat on calcium carbonate between a carbonate and acid. There are no gases on the left hand side, appears on the right. Entropy will increase because of the increased disorder. For example, the production of ammonia, there is a decrease in the number of gaseous molecules and hence a decrease in entropy. There are fewer ways of arranging the energy of the system over those molecules, and so entropy decreases. Alright, let's return to calculating entropy changes in exothermic and endothermic. As mentioned in the beginning, there is a link between a reaction between being exothermic and endothermic, and also we mentioned the term specific temperature entropy values in a previous definition of entropy, and this implies the temperature has a huge impact on whether something is spontaneous or not. Stuff like that. Right. It is possible that energy be transferred from system to surrounding, which is exothermic, or from surrounding to system, which is endothermic. However, because the surrounding is so large compared to the system, often there is just a minute change in temperature or pressure due to the energy exchange, and quite a lot of time we can even ignore it, but not always. And the exact wording is, the surroundings are so large that when energy exchange takes place, there is such a small change in temperature or pressure that we can ignore these. For an exothermic reaction, the energy released to the surrounding increases the number of ways of arranging the energy. Because when we have an exothermic reaction, energy is released to the surroundings increases number of ways of arranging the energy, because we have more energy, and because energy goes into rotation and translation of molecules in the surroundings, and so there is likely to be an increase in entropy and an increased probability of the chemical change occurring spontaneously. And when you talk about endothermic reaction, the energy is absorbed from the surrounding and therefore decreases the number of ways of arranging the energy, and so there is likely to be a decrease in the entropy and a decreased probability of the chemical change occurring spontaneously. And this is interesting. And why is that? Because even if, as mentioned previously, for something to be spontaneous, the total entropy has to be positive. Until now, we've already only been talking about the entropy of the system, and should it be negative, there is still a chance that the reaction is spontaneous. That is only if the overall entropy is positive. And how can it be positive? Because there's another factor, and that is the entropy of the system. And so even if we have a negative entropy of the system, if the entropy of the surroundings is positive, and that can only be positive if the reaction is exothermic, because only then entropy will increase, there's a minute chance the reaction will still occur spontaneously. And this is why exothermic and endothermic reactions have a link with the entropy topic. So total entropy is basically entropy of the system plus entropy of the surroundings, and it is actually the value of the total entropy which determines whether a reaction is feasible or not. Total entropy change, and this is basically what I just told. There is a change in entropy where the reactants and the products have different standard molar entropy values, and we basically convey this as delta S naught, and the total energy involved both the system and the surrounding, and that is why I so clearly tried to explain the difference between them at the beginning of this video. And for the system, reactants and products, we write the entropy change as delta S naught system, and for the surrounding we write it as delta S naught surrounding, and the total entropy change is given by this. And if the total entropy change increases, the entropy change is positive and spontaneous reaction will occur, and if it is negative, the reaction is unlikely to ever occur. And about calculating the entropy change of the system, not the surrounding, just the system, we use a relationship which is basically delta S naught system is equal to S naught of the product minus the S naught of the reactants, and this is very closely resembling the way in which we calculate the delta H of a reaction by using H naught values for products and H naught values for reactants. And there are two things to remember when we use this. Number one, that we have to take into account the stoichiometry of the equation, meaning the number of moles of product, the number of mole of reactants, and correspondingly multiply the values of the entropy of each of the involved substances by the number of moles there are in the balanced chemical equation. And then we have number two, when looking up entropy values in tables of data, we need to choose a data for the correct state, because they have different values depending on the state they are in and even the temperature, but because we're talking about standard, they will be at the same temperature of 298 Kelvin, which is 25 degrees Celsius. Now we have a worked example here, and we're getting a system, delta S naught system, which is in the minus, which shows that the entropy of the system has fallen. We know, however, that calcium reacts spontaneously with oxygen, so the entropy of the surroundings must be playing a huge part and making the total entropy change positive in order for the reaction to be feasible. And we have question number 4, but this is basically easy. You just have to use these standard entropy change values, molar entropy values, to figure out the standard entropy change for the whole of the reaction. Now previously we considered the standard entropy of the system. Let's move onwards to do the entropy change of the surroundings. Let's see if there's anything interesting here. I doubt it. And here Right. Let's go over this. Spontaneous changes occur in one particular direction and not the other. This is something we didn't mention previously, and something you should probably remember. And they take place without the need for work. And exothermic reactions are usually spontaneous, right? And free energy and entropy, right? I guess I already told you this. And should reactions with a positive H value take place spontaneously? Because some salts dissolve readily in water and the solution gets colder and not hotter. And therefore enthalpy is obviously not the only thing in play. Again, endothermic, exothermic. Is there anything interesting over here? Right. A reaction is only spontaneous if it can do work, and it must therefore be, right, we'll talk about this later. Right, exothermic and endothermic. So even if something happens to be endothermic, meaning the surrounding has a negative value, if the positive value of the system is high enough, we would still get a overall positive value. And this is a converse way of looking at things. Why something that is endothermic doesn't mean that it has to be non-spontaneous. It is very much capable of being spontaneous, and this is in direct contradiction to some of the principles that we used to have a long time ago, like about 1.5 centuries or something. Right. Again, this is standard entropy change. We have a whole formula thing going on, introducing total entropy changes. Again, we have this formula over here, and how we're supposed to calculate the entropy change in the surroundings. Let's move onwards. Right, many chemical reactions are accompanied by large enthalpy changes because there's a huge change, and therefore in these scenarios the enthalpy changes change the number of ways of orienting the energy in the surrounding. And therefore in many chemical reactions we cannot ignore the value of the entropy changes in the surroundings because the initial enthalpy change was of such a huge value. And how on earth are we capable of calculating the entropy change of the surroundings? We use this relationship. Delta S naught surroundings is equal to delta H naught reaction over T. Here T is a temperature in the Kelvin. H naught reaction is the enthalpy change, and negative is actually part of the formula and is not the sign of the enthalpy change. So if it is exothermic change, minus will become positive. Right. So when we are performing calculations for the delta S naught of the surroundings, we have to multiply the value of enthalpy change by 1000. Reason being that the usual unit we use is kilojoules per mole, and we have to convert it into joules per mole because the value of the entropy change is joules per Kelvin per mole. And negative sign is actually a part of the equation and not the sign of the enthalpy change. So if the enthalpy change happens to be negative, the whole of this delta H naught over T will become a positive value. So right, the previous calcium into O2 example, in we had a negative value. The value of the surrounding is positive and pretty huge, and this is why the overall entropy change was positive. And what is actually calculation of the total entropy change? We basically sum up the entropy change of the system and the entropy change of the surroundings, and instead of putting in S naught surroundings, we can actually put in the formula. Right, let us discuss entropy and temperature now. 1, 2, 3. This particular video is getting a bit too big. Hopefully you'll bear with me. Right before we had to deal with a few things. Right, we have seen that the entropy change of the surroundings is given by this formula. And if we were to carry out reactions at temperatures above the standard, an increase in temperature would make the entropy change of the surroundings less negative. Reason is because temperature in Kelvin always has a positive value, something you should remember. And because it is denominator, if we increase the value of T, the overall value will fall, and therefore, since negative is still acting on it, it will be less negative. And there are assumptions that we are making, and they are that the value of the H naught is not impacted by change in temperature, even though in reality it does change ever so slightly. And let's have an example of just how important temperature can be, because previously we talked about how the enthalpy change could be really important and it could make the spontaneity of a reaction, how interestingly it could manipulate it. Now let's talk about the temperature. Right. So this is the equation: zinc carbonate going to zinc oxide and CO2. And in both of these, the standard enthalpy of the system has a positive value. However, it is the surroundings that will come into play. At 298 Kelvin, we get a value for the surroundings that is negative, about minus 242.6, and when we sum these two up, we get an overall negative value, and therefore this reaction is unfeasible. However, at a high temperature, say 550 Kelvin, we get a surrounding value which, while still being negative, has a smaller value, and when we sum these two up, we get an overall positive value, and therefore at the higher temperature this reaction is feasible. This is interesting. So there is another general rule of thumb about temperature. Increase in temperature tends to make reactions more feasible. These are exothermic. Honestly, if it were already a negative positive play, things would be different. If it were negative and negative, we would still get the positive value. Alright, moving onwards, you can see that at 298 Kelvin the total entropy change is negative, so the reaction does not occur at this temperature, and at 550 Kelvin the total entropy change happens to be positive, and so the reaction is spontaneous. And when entropy change shows a large positive value, the reaction can be regarded as going to completion and is definitely spontaneous, and if it shows a large decrease, we can deduce that there is very little likelihood of a reaction actually occurring. Now let's take a look at question number 7, the composition of calcium carbonate, and it does not take place at R2P, and explain in terms of entropy changes why heating the calcium carbonate to a higher temperature increases the likelihood. Why? Because basically the bonds of attraction between become weaker, they become at a more disordered state because they're now at a higher temperature, and therefore the entropy has risen. Now in a closed system at high temperature, the reactants and the products are in equilibrium. Closed system, basically one that doesn't have any external influence. Pressure is increased. This is a lot to do with the equilibrium part of it. Because pressure actually influences the value of the enthalpy, because like Schachtner's principle, more pressure we will be going towards the calcium carbonate side of it, there will be a change in the enthalpy, so therefore it will be impacted. And what is the value of the standard total entropy change in equilibrium? It is 0, because the value on either direction is equivalent and negative, and therefore together they will make 0. So now let's talk about entropy, enthalpy changes, and free energy. And all of these things are pretty much interconnected. For an exothermic reaction such as CH4 being combusted, we have a negative value of the enthalpy. But in large negative value of the enthalpy change, the entropy is also similarly negative. Because we have a large negative value of the enthalpy change, again let's go here. If we have a large negative value, negative will become a positive, and because if its value, its magnitude is larger than the entropy, and because that is negative and this is positive, we will have an overall positive value, and therefore this reaction will be feasible. So the total entropy change is positive and the reaction once started is spontaneous. In highly exothermic reactions, where the value of delta H naught reaction is large and negative, the enthalpy change is the driving force of the reaction and not the system's entropy. However, in endothermic reaction, the entropy term tends to be more important because the term delta H naught over T will have a negative value. And if the values of the system and the surrounding are both negative, then the reaction will never be spontaneous. However, if the value of the system is positive and large enough, it can compensate for the negative value of the entropy of surroundings, and so the overall entropy will become positive and the reaction will be spontaneous. Right, and then now we're introducing a whole new term, and that is basically Gibbs free energy. But before that, let's go on to the Chem Guide page. Right, entropy is given the symbol S. Standard entropy is S naught. Entropy changes. Working out entropy changes for a reaction is very simple. You just add up the entropies for everything you end up with and take away the entropies of everything you started with. And this is basically a mathematical representation. Summation of the entropy of the products minus summation of the entropy of the reactants. Again, sigma means summation. In the introductory page, we looked at the following reaction and worked out that there would be a decrease in entropy, but that was based on guesswork. We're comparing the number of gaseous molecules, but if we did have actual values, we could be certain by calculating the overall entropy change. Not really certain because surroundings are there as well, but certainly more certain than the previous one. 1 mole of methane and 2 moles of oxygen. So basically stoichiometry, don't remember you'll have to multiply the value of the entropy of O2 with 2, and 1 mole of CO2 and therefore just 214, and 2 moles of H2 you have to multiply 69.9 by 2, and from 596 you have to from 353.8, which is the product entropy, you'd have to minus the reactant entropy, and you guys get an overall negative value. Now this is a negative value, entropy has fallen. And why is that? Because there is a decrease in the total number of gaseous molecules present. Even though, and this would suggest that this reaction is again not spontaneous, but it is spontaneous. Again, this has to do with the entropy of the surroundings, which will make the overall entropy be positive. And that is all there is to it. Need to practice, right? And now they're introducing total entropy changes. If you only calculate the entropy changes of the reaction, you are leaving out an important factor. Suppose the reaction is exothermic, heat is given off to the surroundings, and that extra heat will increase the entropy of the surroundings. If you add more energy, the number of different possibilities for arranging the energy over the molecules will increase, and the reverse is also true, and therefore you need to consider total entropy change, which is basically summation of entropy of surroundings and entropy of the system. Again, we have the same formula we talked about before. We'll talk about this later. Now, chemists are usually interested in the system of reactants and products rather than having to consider the energy changes with the surroundings. This makes things a lot more complicated. Fortunately for us, there's a way of we can take both into account. So a quantity called Gibbs free energy, or more simply free energy or Gibbs energy, and is represented by a capital G letter. And we can write the previous expression, that is of total entropy change without the entropy of the surrounding portion. That is basically this one. And the temperature is as before in Kelvin. And this is a useful concept because it includes both entropy and enthalpy changes. Again, we must use standard conditions, and these are as before. And if we were to define standard molar Gibbs free energy, it is a free energy change that accompanies the formation of 1 mole of a compound from elements in their standard state. And the symbol is delta G naught with an F in the subscript. Derivation is basically we multiply all of this thing by a minus T, and we are left with this. Right? Multiplication by minus T, delta S, and again minus T, and because of this minus sign will be cut off. Here it would have been introduced and the T would have been cut off, and the S total multiplied by the negative T is actually the Gibbs free energy. And this is derivation. I don't think it's part of the syllabus, but still something pretty interesting for you to know. Now, Gibbs free energy and spontaneous. Whereas for a reaction to be spontaneous, it has to have an overall positive entropy value. The opposite is true when we are considering the Gibbs free energy values. It all has to have a overall negative value. For it to be spontaneous, another thing, the Gibbs free energy of a element is 0, always 0. For reaction to be spontaneous, delta S naught total must be positive. The value of T is always positive on the absolute temperature scale. So applying these signs to the relationship, the value of delta G must be negative for a reaction to be spontaneous. So when a spontaneous reaction occurs at constant temperature and pressure, the Gibbs free energy falls. In the opposite scenario, the entropy would have increased. And if the value of delta G is positive, the reaction is certainly not spontaneous. Now it is about application of the equation. Entropy change of the system has a unit of joule per Kelvin per mole. Enthalpy change is joule per mole. Temperature is in Kelvin. Again, when we're talking about temperature change and reaction, we have to consider these as different terms. We'll consider this in a moment. For a reaction to be spontaneous, delta G must be negative, and temperature can influence the spontaneity of a reaction just as in the delta S total equation. And how can we deduce this? By considering the Gibbs free energy as a combination of two terms, this being the first term and this being the second term. If we are assuming that the value of the enthalpy change does not change with temperature, we can see that the value of T delta S will influence the value of the delta G. So if we have an exothermic reaction, the first term has a negative value. And if the value of the system happens to be positive, that is the entropy of the system happens to be positive, then the second term is negative, and the reaction will most certainly be spontaneous because both the first and the second term are negative. However, if the value of the entropy of the system is negative, the second term is positive, the reaction is likely to be spontaneous if the temperature is low because delta H reaction is more likely to have a greater negative value than the positive value of the second term. That is if the value of the temperature is low, because if the value of the temperature is high, then the overall positive value of T delta S will be huge because we have these two terms being multiplied. So delta G will be negative if the temperature, right? If the temperature is very high, the second term may be positive enough, because again multiplication, to overcome the negative value of the delta H reaction and will make the delta G positive, and therefore the reaction non-spontaneous. Hence, the reaction is less likely to be spontaneous at a higher temperature. And this mirrors what we know about the effect of temperature on equilibrium. For an exothermic reaction, a higher temperature will shift the position of equilibrium in favor of the reactants. And for endothermic, if the value of the system is negative and the second term is positive, the reaction will not occur, because both terms are positive, making the value of the delta G positive. Because negative will result in a positive system value, and delta H is already positive. And if the value of the system is positive and the second term is negative, the reaction is unlikely to be spontaneous if the temperature is low, because delta H naught is likely to have a greater positive value than the negative value of the second term. However, if the temperature is higher, then T into delta S will have a large value, and because this is positive, the negative sign will make it negative, and therefore it is possible that the entirety of the term will have a higher negative value than the other term, which will have a smaller positive value. And this is all that there is to it. And then there is comparison of Gibbs free energy values. And Gibbs free energy calculations, it's the same as the Hess cycle, nothing to sweat over. And Gibbs free energy in work. So if we were to consider delta H to be the positive and we were to rearrange the Gibbs free equation, we could have these: the total energy being composed of two parts, and delta S is the part that is not available to do work, and the Gibbs free energy part is the one that is doing work. And this is basically a summary, and this is all that there is to it. Now let us look at the PPT part. Again, this is something you should know, that the second law of thermodynamics states that entropy tends to a maximum, goes in the direction that will make it maximum. And what else?